So this whole Kuranishi approach was sort of considered true but unreadable for the longest time, until I tried Duza to prove something else to me, and she resorted to the Kuranishi approach, and eventually we realized that we just couldn't make sense of it. So what then happened was that we went semi-public with our things, and then also decided we should maybe, before we really go public, explain to Fukaya and Ono what our problems were. So we asked them a number of questions, and they started to respond to them after we had given talks. So then the interesting question is, who plagiarized from whom? Because at this point there was a 2012 correction by FO Cube of their work, and there's our paper, and I think both parties complain that the other plagiarized from them. I would say we started talking about it before they wrote up anything. I would also say it really doesn't matter. It's about math. So I don't care whether I was there first or not, if at the end of the day we actually have a theorem. So here's the reason that we felt the need to revisit this whole thing from ground up, because analytically the obvious kinds of coordinate changes that we were finding were we had Kuranishi charts, right? There's a section on each of the ambient spaces, the U's, and we had a transition map defined just on an open subset that embeds there. And so then the problem is exactly that this open subset is, that's the piece of identification that happens here. So you'll easily end up getting them. That's the generic happening, is that you have lower dimensional things getting glued into higher dimensional things. So this is really the obvious example to look at, and the quotient topology that we should put on this is really the only topology we can put on this, because we don't have an ambient space. Right? So I constructed these spaces here. The UI were sort of maps with 2 marked points, and the UJs are maps with 4 marked points. So they just don't sit in the same space. So that's why this is the only spaces that there are. They don't sit in something bigger. So we can't take this and take some ambient topology of it. All we can do is take the quotient topology, and to make that very, very rigorous, let me write both UI and UJ project into this space. That's my projections here. And of course there's a composed projection map from the union. So now, a set in the quotient space is open if its pre-image is open. So that means I need to take both pre-images in UI and in UJ to be open. Fairly innocent, right? But now let's see how this space now really becomes locally non-compact near 0. So let's assume by contradiction that there is a compact neighborhood of it. Well, then there will also be compact neighborhood might sound weird, right? By really, usually what we mean by neighborhood is open neighborhood. So in this case, it being a neighborhood of 0 means that there's an open set in U that contains 0, and that's also contained in this compact set K. So let's see what this open set could look like. Right. So 0 is in it. So 0 is in, well, 0 is not in uj here, right? But it is in ui. So that's certainly a point in this set, and so I know what open sets look like here. So I'll certainly have some epsilon ball sit in there, and I might as well take a closed epsilon ball. Alright, so I'll see a little bit of an interval around here that needs to sit in there. But when it sits in there, it also sits in, well, that's not V, that's, well, it's an inverse of V, which means its projection actually sits in V, which means that the inverse of that will then have to sit in this open set that we should have inside the uj. So, right, so here we do end up seeing a little bit of an interval necessarily that comes from there, right? And that's going to need to have some open neighborhood in there, right? So let me take the simplifying example here. I mean, grossly simplifying assumption. Right? I could satisfy this here by saying there's some interval that sits inside V, or inside the pre-image of V. So, for example, I could hope that 0 epsilon times a little interval also minus epsilon epsilon sits inside inverse of V. And so now, well, that does not look, well, hold on. So that, of course, isn't compact because it's open. Right? So I would now like to check whether any open cover of this neighborhood K has a finite subcover. So and so I'm going to make a brutal cover here. So K certainly is covered by the whole space. So I'm taking the whole space, but I'm taking this subset V out. Right. Do I want to do that? No. I just want to take these two intervals out. So the projection of minus epsilon, and the line and this little square in my half space, which leaves me with exactly that stuff to cover. And so now that's something I'm going to cover with a bunch of bad open sets. Essentially, what I'm going to do is I'm going to take Wn to be the graph of square root of n. So everything that lies under this. So I'm going to take the x and y, for which, let's see, y, norm y to the n is less than norm x. So that looks terribly open. Yeah, it contains y equal to 0, certainly. So that all looks good. And eventually, as I let n go to infinity, the sort of any point here I'm going to eventually hit, right? Because the y to the n grows goes to 0 a lot faster than y. So, but that also means if I'm somewhere in my set minus epsilon epsilon here, that's only going to get hit for very large n. So the problem now is if I take the point j of some little x, oh geez, no, sorry, this is y to the n. Y to the n and y, right? So that just about does not lie in Wn. It lies in Wm only when m is bigger than n. So whatever finite subcover of this I took, it's going to stop at some n here, and then this point here for small enough y will lie in this space that I haven't covered yet, and but it's not covered. Right, and I'm going to take, so I should take y less than epsilon here. So that was under this sort of additional assumption that the open set that sits inside of K actually has this form. You can generalize that using, right, so if you had a different domain V here, you can use even more general constructions of the neighborhoods in this curly U. Namely, you can take the whole line Ui, right, and this guy, and then you take everything that sits under the graph of a continuous map. And the crucial thing here is that that continuous map can go to 0 however fast you'd like it to go. Right, so you see all these neighborhoods here. Question.
Can you tell me why something I have in mind is not a locally compact or a compact neighborhood?
Yes.
Okay, so.
Right. So what about the following K? Right? So we're saying we'd like to take a closed set here. Mm-hmm. And then presumably a little bit of this line.
Right.
So let's see. Well, so that would need to contain an open set.
Yep.
Right?
It does.
So it does contain something. Okay. So The question is whether that is compact.
That's not compact in the quotient
Right.
topology.
It is not compact exactly because you can now do, so I can do something similar, right? I can write K as union of everything minus V union a couple of W ends where these guys all go like this. Right. So pretty much whatever, I mean, the game is, the problem is that you have to fix K first, so you're fixing some V that sits inside, so essentially if you just think of this as generating set, you're fixing some function. And the problem is you'll always find infinitely many functions that are smaller than that. So, that's...
Okay, thank you.
Sure.
There's no,
So, this was about having infinitely many functions. The problem is actually also you have sort of uncountably many continuous functions that are positive. And that creates issues with having a countable neighborhood base. So that's the definition of first countability. So that means that, well, this is my favorite formulation of it. That means you have finitely many open sets, little WNs, so that, well, this point 0 that I'd like to have a neighborhood base sits in all of them, and if I have any other open set that contains it, then one of my countably many already set in there. And that's, you prove that by sort of taking an imaginary countable neighborhood base, and from that making a function that is, lower than that, so that the subset that you're getting from that is sort of within all of them, or does not lie within any of them. So, classical proof by contradiction. So. So not only does this is first countability. This defies second countability, and even a more there's another notion that's a little different from second countability. Yes. No, actually, that's a little weaker even than second countability. So in second countability, you would like some statement like this for all open sets, not just for the open sets that contain 0. So the notion of a countably locally finite basis is something where you can replace each of these open sets in this countable set by a huge collection, by possibly uncountable collection of open sets, but they have to be locally finite. So that means whatever point I give you, only finitely many intersect the neighborhood of that point.
Why is it called countably locally finite?
Well, so the thing is, you're taking countably many locally finite collections.
Oh.
Right, so you're not just taking one locally finite collection, you're taking countably many. So in particular, you could take just countably many open sets, because every open set by itself is a finite collection. So the reason I say this is that there is a beautiful characterization of metrizability, which I learned in this process, and there should be something more general that you get out of this than just what doesn't work. So there's a Nagata-Smirnov theorem that says that a topological space is metrizable if and only if it is countably locally finite, and it's regular, meaning you can separate closed sets from points. there's sort of this whole hierarchy of separability axioms in topology, where Hausdorff says you can separate points. This is a little stronger. So, the beauty for me is if you have a Hausdorff space that's second countable, it's certainly metrizable. So, that's the good news. So, but that's this direction, but that direction also metrizability implies countably locally finite bases, and that in turn implies that you actually have to have a countable neighborhood base, because you take 0 as this test point for the finiteness here, and then each of the locally finite collections actually just becomes a finite collection of neighborhoods for 0. Alright, so that implies this, which means since we're not first countable, we're certainly not metrizable either. So, okay, that's the bad news. So, time for some good news. That's something similar, so second countability now means I have a countable neighborhood base. So, well. So for every point and open subset that contains it, I find an n so that, in fact, P lies in this countable collection and the Wn lies in that open set. That's my definition. This is equivalent to saying that you can write O as the union of some subcollection of the Wn's simply by writing it as the union over all P's. If I call this the N sub P of the Wn P. So, right, that's your basic point set topology of the day. Right. And this is what I used when I somehow claimed that when I had perturbed so that I was Hausdorff and compact and transverse, so locally homeomorphic to, and then I'm actually a manifold, because manifolds want to be second countable. So that's that. And the other nifty little lemma in point set topology that we ended up using a lot is something about sort of uniqueness of compact Hausdorff topologies. So if you have one space and you have two different topologies on it that are both compact and Hausdorff, then they're actually the same.
Two nested.
This is nested, right. The crucial thing is that it's nested because this means that the identity from x with tau 2 to x with tau 1 is continuous. And now you'd like to prove that it's also open, and that means you want to move open sets to open sets here, and I think you just need one of the two. I think you need this guy to be compact and that to be Hausdorff. And then you check that bijective continuous maps between a compact space and a Hausdorff space are necessarily open. And that's going to help us because we're going to put a whole lot of different topologies on our spaces, and eventually, you'd have to keep them separated, you know, in all the sort of fuzzy spaces. But eventually we're going to have a perturbed, you know, sort of smooth moduli space, you know, that is locally homorphic and second countable and compact in one topology, but housed off in a different topology. And so then this uniqueness is going to help us. So, right. So that's sort of the topological challenges. So, well, this is mostly, well, there's more challenges and more ideas here. This is, for a start, this is an idea here. You know, this bad topology, you know, with this one bad point, happened by having a coordinate change where I only identified over an open subset. What if I only allow coordinate changes that embed the full set into something bigger? So then this left-hand side here that sticks out wouldn't be there. In particular, the red point wouldn't be there. So that is, in fact, exactly the idea of a Kuranishi structure, rather than sort of the atlas idea that I started to promote. So Kuranishi structure has, for every point in X, a chart. That I'm just going to start calling UP, and then there's, you know, all the extra structure, section, obstruction space, homeomorphism to moduli space. And then for any other Q that is close enough to P, namely that sits in the footprint of the chart P, you would like a coordinate change on the full subset. So it starts with an embedding of UQ into UP. That's a lot more data than the finitely many basic charts I tried to promote, but it seems very nicely organized. So, and I think that's a perfectly fine notion. The two problems, well, not problem. I mean, when you go look at how a Kuranishi structure is actually constructed in any paper, it is constructed from an atlas. They just don't call it an atlas. So, there's a very simple prescription. If you're given an atlas, you know how to choose these charts. But the problem that this has is that, you know, we had this nice order of the subsets, right? So these were the subsets of the so the footprint of the ith chart was the intersection of all the footprints of the basic charts. And so we had this nice order of the overlaps, you know, sort of that induced an order also on our set of charts. And that's something that you're definitely losing, you know, when you take, well, so many of them. So,
how does this avoid that topological thing?
Well, at least in this example, it avoids it.
So,
right, because the UI would have to. So this would be a situation where UQ goes into UP, and UP would be this whole square, but so UQ would now just be this subset.
I mean, presumably we also have some other U or something.
Well, Right. So what then? Well, but it's only going to go into bigger spaces. So the UP is then going to get embedded into some other bigger space.
Is the point that there's actually if the footprints intersect, then one is in the other? Is that the statement?
Right.
That's the condition?
Yes. Yes.
Okay.
That's what you're doing there.
Okay.
Right. Right. So certainly, right. I mean, in particular, FQ is in FP here.
So that location would be allowed if everything was also being embedded into a bigger thing. Right? I mean,
that would.
For instance, you could imagine like a big square that includes that left rectangle and also a
right
one and also a
right.
left one.
Yeah. So what would happen here is actually that you're gonna, the only way that you can capture this point here would be by having, maybe yet another bigger, UR, and a coordinate change from UP to there.
So is it just saying we're like forgetting about the coordinate changes from something that's bigger to something that's smaller, or?
All right. Good. So, so the basic idea here, how to make this from an atlas, is you're gonna sort of take UP to be, this is a lie. Essentially, you're going to take UI, where you pick I to be the maximal subset so that P lies in it. That does not have the right inclusion property, so you need to take sort of shrinkings of your UIs and then their closure, and so there's sort of a little bit, closed open games. But that's essentially the idea. And you can make this so that this sort of P, this map P goes to IP is what is it? Is lower or upper semi-continuous in the right way, so that you're only ever going to get Q in a footprint of P. So this will then directly imply that IQ is a subset of IP. So our atlas will give us these coordinate changes.
But somehow there won't be a point R with this thing and a point Q with this thing and a point P with. So let's see. So I need to take a compact. Right. So I'm going to take some closed subsets here. And what you should imagine is that these closed subsets still cover the whole moduli space. You can always shrink coverings that way, right? So let me call, so these will be VIs that are pre-compact in the UIs. And then the IP is the maximum, so that it's the maximum I, so that P lies, it lies in the footprint of the ith chart and sort of comes from VI closure. Right. And so then the interesting point is this point here. So this P here now lies in VI closure. So U P is now, I think I'm going to take the UI. The UIP, so in this case that's, let's call that the UJ. Right? So this big thing is the UJ and this smaller thing is the UI.
And then I can ask myself, what happens with nearby Q's? I could be on here, or I could be here. Right, and so for this, right, so this uj, and I should take something out that comes from everything that's not part of j. Which is not so important here. No, sorry, that comes from, oh goodness, from bigger ones. Oops. Jeez. Right. Let me say this back here. So this Q here, oh no, maybe I don't have to take anything out right now. So this Q is now going to lie in the footprint of the UP, right? But, right, what I'm going to do is here take a small neighborhood of it. Yeah. So that's going to be my little UQ, that's going to lie in UI. And I can, take its, well, since that's an open set here, I can always fit in another open set that will get me into this, so that I'll have a full inclusion. That only stops working when I'm on the boundary here, right? But when I'm on the boundary,
you can choose to not have
then I'm not in the footprint of P, right? Because the footprint of P is this open set. So that's the crazy part here. But it's all, so bottom line, it's doable. Right. So right. So, but why do I like this partial order though? So that's so in the next step. If I now want to make compatible perturbations, so compatible perturbations now means, let me go back to my EIs and EJs. Right, I had sections or maps, into these vector spaces, and I want to add something to each of them. Right. But I have some overlaps here. And I'd like the whole square to commute. For that, I have, a little problem if I'm imagining uj like this, and I could now have a ui embed one way, oops, ui, and there might be another subset of this j that embeds, similarly, but intersects this in weird ways. So that's possible because maybe the footprint is just this. Or that's the zero set is just that. So the zero set is going to have to lie in the intersection, but so that's not really, oh well, actually, right, and so there could be more zero set here and there.
if the footprints are not ordered as my footprints are in theory. So if I'm now trying to construct these perturbations, it kind of makes sense to go by the partial order that I have. But by that, let's say I and I prime have the same sort of number of elements in them. So then there's no, and they don't have any relation with each other, so then it's not clear which one I would construct first. But if I've constructed both of these perturbations, I need a compatibility on the overlap of these things in here. So that's not a good situation. So what we really like is to have a situation, maybe where, let me write abstractly if ui intersects uj, somewhere in my category via morphisms, then I and j need to be in relation to each other. Which would in this case say that I needs to be, I and I prime need to be in relation to each other. And so, you could achieve that, hopefully, by some kind of shrinking, where in this case, really, it's absolutely superfluous to have both ui and ui prime go all the way through, because uj already covers this zero set. So really, I could shrink my ui to, just a little bit that covers this zero set here, and ui prime to something that covers this bit of the zero set, and leave the rest here to the uj.
So uj would contain the sort of green and blue branching?
Well, it would forget about this, right? So the idea would be, all right, let me just sort of state the ideas here, and then I can say what that is. So what Tuza and I do is we take reductions, so we take sort of smaller subsets. And so the VI here now would just be this part. Oops. And the VJ would just be this part. Oh, this guy does not like me to do so that's the VI prime. And then, right, Vj could be the whole rest. And then I have this nice intersection property. But I've still covered my whole zero set. Right. So, yeah, the idea here is, of course, that the zero set somehow leaks out of the overlap, right? Because the I and I prime have bigger zero sets. Right. So that's one idea. And the sort of upgraded FO cube construction, I think, does two things. That it also it reintroduces a partial order, and then also achieves this separation. And the buzzword here, if you're looking for where that happens, is the construction of a good coordinate system. So that's just to make perturbations that make sense in my categorical framework. Okay, and if I can make them transverse, then I'll get smooth subsets somehow that are glued together in a meaningful way by my transition maps. And then the next question is, why is that compact? Question.
I just want to ask, so the point of this is to when we have a picture like this, that the zero set of whatever perturbed section or unperturbed section we had at near our bad points is going to lie in this one-dimensional thing rather than the higher-dimensional thing.
Right. Well, right. We're going to on the green and the blue thing. You're going to perturb. You're going to get perturbed zero sets.
That are still in the lower
That is,
dimensional.
well, of course, that are in there, right? And so then when you need, so then the next step is you have to extend the perturbation to the yellow stuff. Yeah, and that's the question of how do you extend perturbations then. So there's something called the index condition that will allow you to extend in such a way that the zeros, if they're close to the green and the blue, they're actually on it. But that's, yeah.
And the yellow includes the green and blue, right?
It includes part of the green and blue in our idea.
Okay. So that means that there's a relation between the green and the yellow, right?
Right.
So green is less than yellow.
Green is less than yellow, blue is less than yellow,
Okay.
but green and blue don't have to relate to each other anymore. That's the key.
Right, and because that's why you're going to choose a perturbation for yellow after the one for green.
Right, exactly. Right.
Okay.
Good. And I'm not going to tell you how to do that, because. But since we already have this idea of shrinking, the next question is how do we keep compactness? And I think that's in all approaches really. That's eventually what you'd like is another shrinking. So you take sort of a smaller set whose closure is going to be compact. So this is the picture here, where now I've made sort of this separating pre-compact shrinking. So I prime and I are not in relation to each other. J is bigger. I have all these sort of. Well, I drew them as closed sets, and that should be covering my zero set. And not only that, ideally, I would like to know that if I perturb just a little bit, the perturbed zero set is still going to sit in all these C's. Because then I can, somehow use the piecewise compactness of them to deduce compactness. And that's what Zach already sort of bemoaned here, right? So if my zero set sits in here, right, I can start doing funky stuff. Or maybe it has other things here. Right, this place where the blue thing sort of goes into the green thing. The perturbation is going to come from the blue thing, and now I'm going to have to extend it to the green to keep the zero set inside the blue. Because if I perturb just a little bit here, it's very easy to somehow push zero set, point zero off the blue and into the gray, not into the green. So there's going to be some extra condition here that we call admissibility. So that you actually know that small perturbations will still lie in there. And that's going to mean you have to somehow talk about, near this blue thing, the extension of the perturbation having a certain property. But that means you need a notion of near on the ambient spaces. So, that's, you control the support, and to say near, you need metrics. So that's why we started talking about metric Kuranishi structures. So that's this. Right.
this would all not really be so much of a problem if we were in algebraic geometry. So let me give you a quick excursion. This is not going to help us with the topology, but just a quick excursion of what some sort of initial idea of Kuranishi structures was. They should be closer to algebraic geometry. So all these ambiguities in our choices of domains, that fatten a footprint, and even ambiguities in the coordinate changes, maybe we can quotient out by that. So in particular, all these charts here really, can I maybe just remember, only the footprint, right, which is in my moduli space, and that's the zero set of my different sections in my different charts. Right. Well, how would I do that? There's a idea of a common refinement, so where you might have a smaller set and a bundle. Well, that I think were once isomorphic, and the zero set in here, maybe that should still be a neighborhood of P in your moduli space, but it's allowed to just embed into these zero sets of the two Kuranishi charts, and you'd like to have all of this square commute. So what you're doing there is you're doing two things at the same time. You're allowing sort of germs in the sense of restrict to smaller and smaller neighborhoods of the same footprint. So this V here, U could be equal to U prime, and I just take V being a smaller subset. U prime could just be a subset of U, and then V is equal to U prime, and all I do is I embed here. If it's still a neighborhood of the foot of P, right? So there's restriction, but because I have this external space here, there's also a notion of a diffeomorphism. So one particular allowable thing here would be having a diffeomorphism between the spaces U and U prime that just covers the identity, or that restricts to the identity on the zero set. And I think in algebraic geometry, the zero, these are, all kind of then holomorphic functions. And so really, if you know the zero set, somehow and the germ maybe of your function nearby, you actually know the whole function. And it's more clear that should work for coordinate changes. Right? But here the idea is really that somehow the germ of a chart really sort of uniquely up to some diffeomorphism, determines the little fattened neighborhood. The problem when you do this is that now what are your coordinate changes? Right? So if you now have UP, UQ going into UP by a phi PQ, and this is isomorphic to UQ prime, and this is isomorphic to UP prime by some isomorphisms, then you somehow have to declare phi PQ equivalent to this conjugate guy here. So this is I Q inverse phi PQ I P. So far so good, right?
you then try to write down the cocycle condition, and if you write down the cocycle condition without your brackets around it, it looks very convincing. But when you now try to make sense of it, in terms of equivalences, right, then there should be some way of concatenating these conjugacies. That all still looks very convincing. The problem is that IP, this conjugacy is not necessarily has the same IP as the conjugacy that comes from P and R. So there are two different guys here. And if they're not the same, then the big square here is not going to commute. So, let's see. So in this theory here, phi PQ and phi QR might compose to the phi PR, but when I compose these two, I might not get something that's conjugate to the phi PR. So that's something that I think was sort of quietly discovered and resulted in some sort of quiet changes without people really saying, look, that was a problem. So Joyce did something where he tied these two a little together, so he only allows sort of isomorphisms of a very specific type, so that then somehow there is a composition of these two with those two that gives you something here. So he makes sort of a two-categorical structure out of this. So you have to keep track of the isomorphisms. That's the notion of d-orbifold, which I think is algebraically the right idea. The question is whether it has geometric applications. And with the addition of Ota and O, they just dropped this. They just said, we're not going to do this. Diffeomorphism, these are the identities. I think all they do quotient by is sort of common refinement in the really sort of germy way. So, but I think, so these two isomorphisms here in algebraic geometry would probably be determined by somehow the ambient structure that's already there. And so my guess is that in algebraic geometry these would be forced to be the same. And so then this would work. So, well, this does work. Just I can't read enough algebraic geometry to find whether that's really what's happening. All right. Good. So that's the list of problems and ideas. And with that, I was going to give you more of a brief idea of what our end of the story looks like with that. So, the good news is that the notion of a Kuranishi atlas really is what we've talked about. We just have additional words we added before, just because we like to keep track of its actual properties. And there's a version with isotropy. I'm not going to, it's here for those who want to know this. But basic structure is you have this sort of covering by some basic charts, right? And then we have the transition data as we constructed it, analytically, where you have sort of these nice sum charts. This is where somehow additivity comes in and saying that the sum charts come from summing the obstruction spaces. And the coordinate changes, are still now these embeddings of open subsets. Then there's an index condition that I would like this d phi to identify the kernels of the linearized sections and the co-kernels of I and j. That on the one hand implies that the index is going to stay the same. That also implies something that's called the tangent bundle condition in the Kuranishi world, in the Kuranishi structure world. And that's something you really want when you put orientations on. And you need that also actually to sort of extend transversality results. Questions?
Well, I'm just confused by the statement that d phi should identify the kernel and the co-kernel.
Right. Well, okay. So in the tangent space to U, and the tangent space to Uj, you certainly have the kernel of dsi and kernel of dsj.
Mm-hmm.
And then the co-kernel, of course, sits in EI, right? Or you could pick a representative in EI. When I say phi ij, I mean, you lift here.
But I mean, so this
part
means
of the structure.
that the Fredholm index of S is 0.
No. It just means that the difference. It doesn't. Okay, that's bad wording. So d phi ij, it identifies the kernel of dsi with the kernel of dsj, and the co-kernel of dsi with the co-kernel of dsj.
Okay, great.
Yeah, kernels and co-kernels.
Thank you.
Right. That means that the Fredholm index of Si is the same thing as the Fredholm index of Sj. Good catch. And what we said we got naturally is this weak co-cycle condition for our coordinate changes. So that's what we call a weak additive Kuranishi atlas, and we only put it on spaces that are compact and metrizable, because I believe we use the metrizability at some point. And then this is one place where interesting things happen. So we say that when we have one of these weak additive Kuranishi atlases, then we can shrink to find a metrizable tame Kuranishi atlas. So shrinking is just taking smaller domains in all my Kuranishi charts. And that has a whole lot of nice properties. For example, this is slightly different wording here. So the projection maps from a UI to the quotient of all the UIs, not the phi ij's. A priori it wasn't clear that that's anything nice, but we can make all these projection maps homeomorphisms. So that's nice. And then this whole
construction also always has to go together with the fact that somehow any two such shrinkings we need to be cobordant. Because in the end you want to get, something from the weak Kuranishi atlas, not from a weak Kuranishi atlas together with a shrinking. So all the choices that we make should not be visible in the end. Let me not go at that. So with that, what we want is a regularization theorem. So, and we're now looking what are the perturbations, how do I get compact smooth zero sets and why are they cobordant? And here is that theorem. So good thing is, okay, tame Kuranishi atlas, whatever it is, you now also need something called a reduction. And then what we would like is something called a pre-compact transverse perturbation. But once you have that, your zero set will be, smooth d-dimensional manifold. And then there are different quotient topologies on it, right? So it could have the quotient topology, and there's a subspace topology from it sitting in the big ambient space that I got from gluing all my U's together. That's this K here. So compactness is the same thing. Right? So that's what gives me smooth manifolds that are compact, which now means how do I get pre-compact transverse groups? Transverse perturbations, and that's where the nightmare begins. So what we can really prove is we're making VC delta sigma adapted perturbations, where there's a reduced space V that sort of separates things so that I can iteratively construct perturbations, and the C governs the compactness. There's a sigma that controls, right, so there's a delta that controls, you now need somehow finitely many little reductions in between C and V so that you can, keep shrinking as you construct. So that's what your delta does. And the sigma then controls the size of your perturbations that you need in order to make sure you're staying in the zero set stays in C. And so that's a pretty cumbersome construction, but it works. The problem is that now it depends on all these choices, and then when you go and try to prove a cobordism theorem, you need to talk about metric tame Kuranishi cobordisms, and when you're given adapted perturbations on the boundary, you need to extend them to appropriately adapted perturbations in the interior with all this extra data. And then there's a bunch more things. But so there are theorems that are only propositions because they're so ugly, but they look very similar to these things, these two.
So if I take two different perturbations which are adapted to different four tuples, then that theorem that you just displayed still, their zero sets will be cobordant, right?
Right. So there's a long story here that says
You know, when you have different data, so the different data that you choose from your weak additive Kuranishi structure, all the possible different data is cobordant, which means there are Kuranishi cobordisms with such data that on the boundary restricts to the different data.
Okay.
Right? And then
So that implies the same.
yes, yeah. So it's ugly. Yeah. It's ugly, I believe it's true, but I really would need some checking. So, I'll take votes whether you want to see more of those details after spring break.